Welcome back. I'm Dr. Nuoshu. A one-sentence preview of this lecture will be, how should we trust and use a model? We'll discuss the following topics sequentially: expected value based usage, ranking based usage, ROC and AUC, cutoff determinations. We will again go straight to an example to introduce the notion of expected value. So here we have a lottery A, which has 1% chance of winning you $1,000. How much should you be willing to pay for it? We have another lottery ticket, let's call it lottery B. It has 1% chance of winning you $1,000, 5% chance of winning $100, and 10% chance of winning $10. How much should you be willing to pay for it this time? Now pause and ponder about it for a while. For lottery A, many will come up with $10 by doing the following, which is multiply 1% by 1,000. That gives you $10. It makes intuitive sense. How about lottery B? You will probably be more reluctant, but if we extend the logic that we use for lottery A here on lottery B, then we should have something like this one. I multiply 1% by 1,000, 5% by 100, 10% by 10, and I will sum them up. I would get 16. So are these approaches correct? It's difficult to tell if we are only given one ticket because both lotteries have multiple outcomes and each outcome is associated with different payoff value. But by getting only one ticket, only one of those multiple outcomes can realize with only one lottery ticket. So what if we have 100 tickets of each? Let's look at that situation. So for 100 tickets of lottery A, we know one of them is going to earn us $1,000. And the remaining 99 tickets is going to earn nothing. Therefore, if I calculate the total payoff of 100 tickets, it should be in the parentheses. So if I divide that total payoff by 100, then it should give me the average earning per ticket. Therefore, you should be willing to pay up to $10 to pay for each ticket for lottery A. Let's also look at lottery B. So if I purchase 100 tickets of lottery B, I know one of them is going to earn me $1,000, 5 of them is going to earn me $100, 10 of them is going to earn me $10, and the remaining 84 tickets is going to earn me nothing. Again, so this sum should describe the total earning if I purchase 100 tickets of B. And by dividing that sum by 100, that gives me the average value per ticket. Therefore, you should be willing to pay up to $16 for lottery B. So this notion of average earning in this context is referred to as the expected value in the data science or statistic jargons. And the logic behind calculating this average earning for lottery B also shows a general rule of how to calculate expected value. So if we rearrange this calculation a little bit here, so what is done here is I would distribute this divided by 100 into each of the terms within the parentheses. So I'll just get rid of the parentheses, and then now, so this shows that the general rule of calculating expectation is to recognize there are, in this case, we have 4 different outcomes, 4 different payoff values for debt tickets, and each is associated with a corresponding probability. So the general rule of calculating expected value for this kind of situation is to multiply the outcomes with its associated probability and then add them together. And that's how you calculate expected value. You first need to identify what are the different outcomes. You need to then calculate or estimate what are the associated probability associated with each outcome, and then you use this formula to calculate the expected value. Let's now look at how the notion of expected value can help us to provide some guidance as to how to use a model with an example. Say we have a model that can help us predict what is the probability of a customer's likelihood to respond to a marketing offer. Now the question becomes, how should we decide whom to target? Let's run through 2 scenarios. In the first scenario, we have unlimited budget. That means we can target as many customers as we want, as long as each one of them is profitable. So how should we go about deciding what is who should target? So let's say the probability of a customer responding is denoted as P. Therefore, non-responding would be 1 minus P. Let's further assume if a customer responded to an offer, the revenue from selling that product is $100. Let's say the mailing cost of sending out an offer to a customer is $1. Now let's apply the notion of expected value to calculate what is the average profit to target a customer. Now there are 2 outcomes. One is you targeted someone and someone responded. What is the net profit for that outcome? Since we know the revenue is $100 and it takes $1 to send out that offer, therefore the net profit will be 100 minus 1. And the other outcome would be sending out an offer, but the customer did not respond. And in that case, we lose $1 in the mailing cost. So therefore, the 2 outcomes are $99 and negative $1, and the associated probability is P here and 1 minus P. So our goal is to calculate what is the P value, what is the value of P, so that the expected value of targeting that customer is going to be greater than or equal to 0. So this just requires a little bit of simple calculation. The P turns out to be 1%. Now, therefore, our decision rule will be target all the people as long as the predicted response rate is greater than or equal to 1%. So in this scenario, a trustworthy model will be the one that provides accurate prediction in terms of probability. So in other words, using the graph from previous module, the predicted curve, which is the blue curve, should closely trace the actual probability curve, the red one. So this can be easily validated by applying the model, the blue curve, on a training data set from which you can derive the red curve. Now let's move on to the scenario 2, where instead of having unlimited budget, we only have $10,000 for mailing. Remember, we have the mailing cost for each customer is $1. So now just pause a little bit and think about how is scenario 2 different from scenario 1. So in this case, it seems reasonable that we should mail the top 10,000 customers with the highest predictive probability in hope of getting the most response. So in this scenario, we are not as concerned for the accuracy of predictive probability. What we care more is the ranking ability of a model. In other words, if I have a predictive probability for customer A, and if there's a real probability, that I would denote it as the real value, I am not as concerned as these two numbers need to be really close to each other as I was concerned about in the scenario 1. But this time, what I'm more concerned about is if I have a probability estimation for the customer B, and if based on our model I have P sub A greater than P sub B, meaning according to our estimation, A is more likely to respond than B, which is expressed here, then in reality A actually has a higher probability to respond than B will. This should lead to this. So it might seem subtle, but it's quite a departure from scenario 1. Now we're going to next talk about how to measure the ranking ability of a classification model. In order to introduce how we can measure the ranking ability of a classification model, we need to take a look at another representation of the confusion matrix, whose terminology can be traced to medical diagnosis. Therefore, we'll now go to Excel to look at an example of classification applied in colorectal cancer diagnosis with biomarkers. We collected a sample of patients with biomarkers such as AFP, CEA in the first 4 columns, i.e. the attributes. A biomarker typically measures the level of some protein such as CEA in the blood or tissue, the rise of which is caused or associated by certain medical conditions. All these patients underwent surgery, and that's how we obtain the 5th column, the target variable. Here, Y indicates an instance or a patient is a cancerous case. 0 indicates it's a benign case. So we are interested to see whether or not we can use these biomarkers to predict the target variable, based on which we can prescribe treatments. I'll use a number of Excel functions here, but constrained by time, I can only mention them briefly. You can always Google them for more detailed instruction later. I use the count function to calculate the total number of instances in this dataset. I use sum function to count how many ones. Again, 1 indicates a cancerous case, 0 indicates a benign case. And the total number of 0 is simply the difference of the two. So out of 255 patients, 111 of them were diagnosed with colorectal cancer, and 144 of them benign after surgery. The sixth column is a logistic regression model. We can obtain these intercepts and slopes for each attribute from either Weka or any other software that provides logistic regression. Also notice in this column that I have sorted all the instances in the descending order of predicted probability of being 1. Let's now assume this is how a doctor will use such a model. Above a certain risk level, which is expressed as the probability of being 1, we call such a threshold a cutoff point. Above this cutoff point, a patient will be directly sent to surgery. Below it, a patient will be asked to come back in 3 months for another blood test. So how would you go about determining such a threshold? Let's get started by arbitrarily choosing 90% as the cutoff threshold. In other words, we'll call all these 12 patients that have predicted probability about 90% as a positive case of rectal cancer, and below that value, all these patients are considered as negative cases for cancer. Notice the reason I know it's 12 patients is by looking at this number, count 12. Also notice out of the 12 patients that exceed the threshold, 11 of them are actual positive case. 1 is an actual negative case. Let's now figure out what the associated confusion matrix with that cutoff should look like. So I started with these two numbers. This number is the actual positive case, which is 111, which we calculated earlier. And this is the actual negative case, 145. And they add to the total numbers of instances at 255. Then this is the next number I figure out by cutting at 90%. Using the Excel sheet, we know there were 12 patients above that 90% cutoff. And we also know that out of the 12 patients, 11 of them are truly positive. 1 of them is actually negative. And also based on our knowledge of confusion matrix, I know these two numbers should add to 111. By subtract 11 from 111, that's how I get 100. Similarly, by subtract 1 from 145, that's how I got 143. If this number is subtracting 12 from 255. Now we're going to go one step further than our previous treatment on confusion matrix by naming each of the 4 cells. We call this top left cell. These are the instances that we predicted as positive and are truly positive. We call them true positive. We call this cell false positive because these are the instances that we predicted as positive but actually are negative. Therefore, we falsely predicted them as positive. Therefore, false positive. and we call this cell true negative, because these are the instances that are truly negative and are correctly predicted as negative by our model with the cutoff of 90%. And this cell is called false negative, because these are the positive cases that are falsely predicted as negative. I will further define two more percentages. The first one is called true positive rate. True positive rate. It is defined as the true positive case divided by the total actual positive cases. So in this case, it's going to be 11 over 111. Again, it shows of all the true positive cases, how many of them are correctly classified as positive. The second percentage is called a false positive rate. It's defined as the ratio between the false positive cases divided by total number of negative cases. In this case, it's going to be 1 divided by 144. Again, this shows of all the negative cases, how many of them are falsely classified as positive. Then again, we can define the same accuracy measure that we have defined before, which is the ratio between the two main diagonal cells divided by the total number of instances. So in this case, it's going to be 11 plus 143 divided by 255. Again, the confusion matrix, the 4 different cells, the 2 new percentage we just introduced, and also the accuracy. All these numbers are derived using the model coupled with this cutoff point that we somewhat arbitrarily selected as 90%. But you might think in your head already, why 90%? The truth is that we do not know. So what we're going to do is we're going to try many other cutoff points. Therefore, we need to ask Excel to calculate all these calculations that I just showed you, instead of relying on us to do that manually for each potential cutoff points. So now let's walk through this Excel example to show how can we use Excel functionality to calculate the confusion matrix and the 3 ratios. So I put TP2 stands for true positive, false positive, true negative, false negative, false positive rate, true positive rate, and also accuracy. So I'm going to use Excel and use the appropriate formula to do the calculation. So earlier we decided to cut at above 90%. So here, remember earlier we said the true positive cases are 11 of them, because above these cutoff points there were 11 ones. So essentially we just need to find an Excel function that can calculate how many ones are in this range. And the function that can fulfill that function is called COUNTIF. So I need to first specify a range that I need to count. In this case it will be here. And the criteria is 1. I want to count within that range how many ones are there. So it shows 11. And similarly, in this case, how many false positive cases? Remember earlier we said there's 1. The reason it's 1 is because in that range there's 1 0. So the false positive cases will be those instances that have 0 within that range, which is above the cutoff. So we use the same function countif, and then we select the same range. But in this case, our criteria becomes 0. So now how about true negative? Again, true negative are the negative cases. And again, false positive are also the actual negative cases. Therefore, we know these two numbers should add to the total true negative cases, which is here 144 that we calculated earlier. Therefore, the value of this cell would be 144 minus 1. In this case, false negative, that means they are actual positive case. And we also know the two positive cases plus the false negative cases should equal to the actual positive cases, which is 111. Therefore, in this cell, it should equal to this cell minus true positive cases. Now, how about true positive rate? As I defined earlier, the true positive cases are the true positive rate is the ratio between the true positive cases divided by the total actual positive cases. Therefore, this can be easily accomplished by this cell divided by total number of positive cases. How about false positive case? How about false positive rate? It's defined as the number of false positive cases divided by the actual negative cases. Therefore, it is this divided by this cell. Accuracy is simply the correct prediction, which is the true positive plus true negative. Divided by total number of instances, which is stored in this cell. So now if we want to try a different cutoff point, say here, then we should be able to just copy all the Excel formula to these cells. For example, let me copy this cell to here. Now, here is a little bit of Excel 101. Earlier, the example, if we click, we know this is the correct range that we wanted to specify. But now look at the copied cell. The range stays at the same size, but then now this time it actually included this header cell that is actually not what we wanted. So this tells you that in using Excel formula, the range specified is relative to where the cell is. So in order to lock the top cell at this row, what we need to do is to go back to the first formula and put a $sign before 5 to tell Excel I will lock the top of the range at the 5th row. And similarly, I need to do the same thing on every other cells that we just fill in formulas to make sure that we reference the right places and locking the appropriate cells by using the $signs. I will quickly do that now. So I just put in the $sign at the right place. You can verify by yourself later. So what I need to do is to copy all these formula in this range to fill all these white spaces, because each row represents a potential cutoff point. So what I would do is I would right click and say copy, and then I will select the target range where I want to copy those formula into by doing the following. I select the top left cell of the range, and then I will press down Shift key, and then I will select the bottom right cell of the range. So that's the way I tell Excel these are the cells I want to copy the formula to. Then I will right click and say paste. And similarly, I would do that for the remaining white space. I will select the top left cell, and then I would move to the bottom left. In this case, it's going to be column P. I will press down Shift, and then I will select bottom right. Now I will right click and say paste again. So using the method of click on top left cells, pressing down Shift, and click on the bottom right cell to select a range is very advantageous when you need to deal with a data set that might be a lot bigger than this one, because this one only have 255 instances. Imagine you have a data set that had 20,000 instances. It would be a lot difficult to select them without using that method. I'm now going to do a few things also to accommodate the possibility of working on a huge data set. So what I'm going to do is I'm going to click this cell, this row. I will go to view, I will click freeze panes. Once I do that, now when I scroll, the top section stays put. Now I am going to insert a bunch of empty cells. So now what I have here is I'm going to create a space where I can place a bunch of, actually 2 graphs I'm going to create later. The first graph I'm going to create is a scatter plot. I will use this column as the X coordinate, this column as the Y coordinate, to create a scatter plot. So what I would do is, again, I will click the top left cell, I would go all the way down and press the Shift key down to select the bottom right cell. So this is a range where I want to create a scatter plot on. Then I will go to Insert, I will select Scatter Plot. So this is now the scatter plot that is based on these 2 columns of data. Again, every row represents a point. This is the X coordinate, this is the Y coordinate. So now I'm going to change this chart title to ROC, because the name of this kind of chart is called ROC curve. I will come back to talk a little bit more about ROC curve. Now I'm going to create a second plot on accuracy. So this time, I will select the first cell and the last cell by pressing down Shift key, and then I will go to Insert, but this time it's only one number, so it's not going to be a scatter plot, because again, scatter plots requires 2 coordinates to describe a point in a 2-dimensional space. So in this case, it has to be a line plot. Now I'm going to move this plot, the graph here at the top section of the sheet. I would again change this to accuracy. The reason I created these two graphs is they provide answers to the two questions we have had so far. The first one is how to find the best cutoff point. So if you look at this chart, so the accuracy represents if we keep moving the cutoff to a lower and lower probability. So this shows us the accuracy first goes up, then goes down. So I can find the cutoff point that represents the highest accuracy. And that cutoff point seems to be a reasonable choice of cutoff. So I'm going to use another function called max. I want to find out what is the highest accuracy achievable. So it tells me the highest number in this column is 74.9%. So I just need to scroll down and find that number. It's right here. So this tells me if I use cutoff point as 0.46 or any value that is greater than or equal to 46% chance of being 1 as the cutoff, again, meaning above that point I will classify all the instances as positive. Below that point I will classify all the instances as negative. I should be able to achieve the highest accuracy in terms of diagnosis. The second graph, ROC curve, provides a tool to the question we started earlier, which is how can we measure the ranking ability of a classification model. So I would say quite a few things about this curve, but for now, notice one thing, that the maximum value for both axes are 1. Therefore, this square, which is 1 by 1, this square should have the area of 1. And we'd actually call this area underneath the curve AUC, which stands for area underneath the curve. I'm going to make a few statements about ROC curve and AUC, which is the area underneath the ROC curve, and then I will come back to explain why they are true. Number one is a perfectly ranking classification model will produce an ROC curve that goes straight up the y-axis like this and then go across the x-axis horizontally. Therefore, its associated AUC would be the whole square, which has the area of 1. Number two, if we create an ROC curve not using a predicted probability, but using a sequence of random number, therefore it's not predictive at all, we will have an ROC curve that goes like this, a 45-degree straight line. Therefore, its associated AUC will be half of this square, which is 0.5. Number three, a realistic model will be somewhere in between these two extreme cases, like this blue line that we acquired from running the medical diagnosis example, with an AUC somewhere between these two values. Therefore, AUC can serve as a numeric index to show how well a classification model can rank. Let's now look at a simplified case with 100 100 positive cases, 100 positive instances, and then 100 negative instances to reason why those statements are true. So for a perfect model, if I sort the instances in a descending order of probability, what should happen for a perfect model situation? If it's a perfect model, then by sorting them descendingly, all the 100 positive instances should flow on top. Whereas all the 100 negative instances should sink to the bottom, like this. That's what the perfect model should do. In other words, the lowest probability associated with the positive instance for this one should still have a higher probability than the highest probability associated with a negative instance for this one. Now let's work out the true positive rate and false positive rate. Let's look at the definition of true positive rate and false positive rate again. So it's defined, true positive rate is defined as true positive counts, which are the ones that is above cutoff, divided by total number of actual positive. In this case, it's 100, which is a fixed number for the denominator. Let's look at false positive rate. It's defined as false positive count. Again, in this case, it's a number of zeros that are above cutoff divided by the true negative cases. In this case, it's a fixed number at 100. So once we are clear about this, we can look at this table for a perfect model. So if we count at the first instance, number 1 above cutoff will be 1. Again, remember the denominator always stays as 100. The number of 0 above cutoff will be 0. So if we move the cutoff down by 1 position, then we will see that there are 2 ones above cutoff. And notice this number is going to stay as 0. So if you go all the way until until having cutoff right below the 100th positive instance, you should get 100 over 100, and this number should stay at 0. Then if you move down the cutoff 1 more position, this number stays the same because we have included all the 102 positive case. So this number is going to stay as 100, and again denominator stays as 102. But now how many zeros we have above cutoff? It will be 1. So it will be 1 over 100. And then this sequence of number is going to stay as 1 all the way to the end. And how about if we keep moving it down another position? This time we would have 2 zeros above cutoff. Therefore you would have 2 over 100. And you can see the trend continues until you get to 100 over 100, which is 1. So now if we plot these 2 columns as a sequence of coordinates, then you will see this number will go, these points will go first up the y-axis, because the x coordinate stays at 0, but the y coordinate starts from 0, 1 over 100, 2 over 100, all the way to 1. That's how the first segment of the line is the vertical line. And then now the y-axis stays as 1, but then the x-axis starting to increase by the increment of 1 over 100. Therefore, it should go this way. And that's why a perfectly ranking model should produce a ROC curve that goes up and across, resulting in an AUC value of 1. Now I want you to pause the video and reason why a completely unpredictive or useless model would produce a 45-degree straight line of ROC curve and therefore resulting in AUC equal to 0.5 by following this example to fill out this second table and share it in the discussion board. We can also quickly verify those statements by using the Excel as an example. So this ROC curve was created by sorting the instances with the descending order of this predictive probability based on a logistic regression model. Now we can choose to use our columns to sort the instances to create different ROC curves. For example, this time I'm going to use the class as the column to sort. So if I choose largest to smallest, then what happens is all the ones is going to float to top and zeros is going to sink to the bottom. So essentially it would provide the same sorting result as a perfect ranking model. So let's look at what ROC curve will look like. It will look exactly like what we expected. And we can try to use another column to sort it. For example, let's pick CA50. CA50 is the one attribute that has the smallest slope. So I can infer it among all the attributes, it has least amount of predictive power. And let's see what the ROC curve look like. So it's a lot closer to the 45-degree line that we discussed earlier. So this concludes our third lecture in predictive modeling.